welcome to this problem walkthrough. In this session, we'll tackle the problem number 430, flatten a multilevel doubly linked list. This is a fascinating challenge that tests our understanding of linked list traversal and recursion. Let's jump in and explore the solution approaches together. In this problem, you are given a doubly linked list where each node contains the typical next and previous pointers, but there's also an additional child pointer. This child pointer can lead to another doubly linked list, effectively creating a multilevel data structure. These child lists can themselves have children, forming a hierarchy of linked lists. The goal is to flatten this multilevel structure into a single-level doubly linked list. To achieve this, we must insert the child nodes of a given node immediately after that node, and recursively process any child lists to include them in the main sequence. Importantly, the flattened list should maintain the relative order of nodes as they appeared in the original multilevel structure. To better understand the problem, let's look at an example. Imagine we have a doubly linked list where the main sequence starts with nodes 1, 2, 3, and so on. Node 3 has a child pointer leading to another list with nodes 7, 8, 9, and 10. Additionally, node 8 within this child list has its own child pointer leading to nodes 11 and 12. Our task is to flatten this structure so that all child nodes are incorporated into the main list. The output for this example would be a single-level list, 1, 2, 3, followed by the nodes from 3's child list, which are 7, 8, 11, 12, 9, and 10. Finally, the remaining nodes from the original main sequence, starting with 4, are appended, preserving the overall order. Now consider another example to solidify the concept. Here, the main sequence consists of nodes 1 and 2, but node 1 has a child pointer leading to a separate list with nodes 3, 4, and 5. Flattening this structure involves inserting the child list of node 1 directly after it. The resulting list would start with 1, then include nodes 3, 4, and 5 from the child list, and finally, node 2 from the original sequence. This demonstrates how child lists are recursively flattened and inserted while maintaining the original order. There are several important constraints and edge cases to consider. The number of nodes in the list can range from 0 to 10,000, and each node has a unique integer value between 1 and 100,000. The child pointers may be null, and the structure is guaranteed to be valid, meaning there are no circular references. For edge cases, if the input list is empty, the output should also be empty. If no node has a child pointer, the output list should remain identical to the input. On the other hand, if every node has a child pointer, the solution must recursively handle all nested levels. Finally, the solution must be efficient enough to handle very large input sizes. To start, one approach we might consider is a brute force method that relies on iterative traversal combined with recursive flattening of any child lists. The intuition here is simple. As we traverse the main doubly linked list, whenever we encounter a node with a child pointer, we recursively flatten the child list and append it to the current list. The process involves inserting the flattened child list between the current node and its next node, while ensuring the next and previous pointers are updated to maintain the doubly linked structure. However, this approach has significant drawbacks. Although it's straightforward, the recursive nature can lead to redundant work, as already flattened portions might be traversed again. This inefficiency is reflected in its time complexity, which can reach n squared, in the worst case for deeply nested structures. Additionally, the space complexity depends on the maximum depth of the recursion, making it O(d). These limitations make this approach less suitable for large or deeply nested lists. Now, to address the inefficiencies of the brute force method, we can adopt an optimized approach using an iterative depth-first search with a stack. The intuition behind this strategy is to simulate the depth-first traversal process iteratively, which avoids redundant work and eliminates the need for recursion. Using a stack allows us to efficiently backtrack when a nested structure is fully processed, ensuring that we only traverse each node once. A few key observations make this approach effective. First, since the input is a doubly linked list, we must preserve both next and previous pointers while flattening. Second, the child pointer serves as a clear indicator of nested structures that need to be flattened and sequentially inserted into the main list. By modifying the list in place through pointer rearrangement, we ensure that no additional nodes are created, making this approach both efficient and space-conscious. The steps for implementing the iterative DFS with a stack are straightforward. We begin by initializing a stack and pushing the head of the list onto it. While the stack is not empty, we pop the top node and process it. If the node has a next pointer, we push that onto the stack to revisit later. Similarly, if the node has a child pointer, we push the child onto the stack, flatten the child list by connecting it to the current node, and sever the child pointer. Throughout this process, we ensure that the next and previous pointers are updated correctly to maintain the doubly linked list structure. This continues until the stack is empty, indicating that all nodes have been processed. The modified head of the list is then returned as the result. In terms of complexity, this approach is efficient, with a time complexity of O(n), where n is the total number of nodes, as each node is visited exactly once. The space complexity is O(d), where d is the maximum depth of the multilevel structure, as the stack size depends on the depth of nesting. When considering trade-offs and alternatives, it's worth mentioning a few other approaches. Recursive DFS is similar to the stack-based iterative DFS but relies on the implicit call stack for backtracking. While this approach has the same time complexity of O(n), its space complexity is also O(d), which can lead to stack overflow for deeply nested structures. Another alternative is breadth-first search, or BFS, which processes nodes level by level. While BFS also has a time complexity of O(n), its space complexity depends on the maximum width of the list, which can sometimes be less efficient for this problem. Ultimately, the chosen strategy is the iterative DFS with a stack. This approach is efficient, robust, and avoids the risk of stack overflow, making it well-suited for deeply nested structures. It balances simplicity and performance, modifies the list in place, and meets the problem's requirements effectively, making it the ideal choice among the available options. To begin with, the problem asks us to flatten a multilevel doubly linked list. In this type of list, each node not only points to its next node but may also have a child pointer, leading to another doubly linked list. The goal is to transform this complex, nested structure into a single-level doubly linked list while preserving the original sequence of nodes. One straightforward approach to solving this problem is through iterative traversal combined with separate processing of the child lists. The idea is to traverse the list node by node, and whenever a child pointer is encountered, we handle it by flattening the child list and appending it to the main list. This ensures that the entire structure is processed in a systematic and in-place manner. The first step involves initializing a traversal process. Starting at the head of the list, we use a pointer, referred to as current, to iterate through the nodes one by one. Now, the traversal begins. While the current pointer is not null, we check if the current node has a child pointer. If a child is present, we save the next node in the sequence to ensure that it can be reconnected later, as the child list will temporarily interrupt the main sequence. Next, the child list is flattened recursively, starting from the node pointed to by current.child. Once this child list is flattened, we attach it directly to the current node by updating the next pointer of the current node to point to the head of the flattened child list. Additionally, the previous pointer of the child list's head is updated to point back to the current node. Once the child list is integrated, the child pointer of the current node is set to null, as the child structure is now part of the main list. To complete the process, we traverse to the end of the newly added child list and reconnect the saved next node to the tail of the child list. Both next and previous pointers are updated accordingly to maintain the integrity of the doubly linked list structure. Finally, the current pointer is advanced to the next node, which could either be the tail of the child list or the original next node. This process is repeated iteratively until all nodes and their children have been processed. At the end of the traversal, the doubly linked list will be fully flattened into a single-level structure. A key insight here is the recursive nature of this algorithm. Each child list is independently flattened before being integrated into the main list, making it possible to handle multiple levels of nesting efficiently. The algorithm also modifies the list in place, leveraging the existing next and previous pointers. This eliminates the need for additional data structures like stacks or queues, keeping the space usage minimal. It's important to account for edge cases as well. For instance, if a node doesn't have a child, we simply skip to the next node. Similarly, if a node is the last in its level, care should be taken to reconnect it properly to avoid losing access to subsequent nodes. Special cases, such as an already flat list or an empty list, are handled gracefully by this approach. Let's take a closer look at the data structures involved in this solution. At the core, we have the doubly linked list itself, where each node contains 4 pointers, val for the value, next and previous 4 forward and backward traversal, and child 4 pointing to a nested child list. The previous pointer is particularly useful during the reconnection process, as it ensures that we can traverse backward to maintain the doubly linked structure. Additionally, the recursive nature of the algorithm relies on an implicit stack, which is managed by the function call stack. This stack allows the algorithm to keep track of the current state at each level of nesting. The depth of this stack corresponds to the maximum level of nested child pointers in the list. Analyzing the algorithm's complexity, we observe that the time complexity is O(n), where n is the total number of nodes in the multilevel doubly linked list. Each node is visited exactly once, and its child list, if present, is flattened and integrated in linear time. As for space complexity, the implicit recursive stack is the primary contributor. The maximum depth of this stack is determined by the level of nesting in the list, which we denote as d. Thus, the space complexity is O(d). While the algorithm is efficient in terms of time, the recursive stack space can be a concern for deeply nested structures. To address potential drawbacks of the recursive approach, we can consider some optimizations. First, by using an iterative approach, we can simulate recursion with an explicit stack. This eliminates the risk of stack overflow for deeply nested lists, while still maintaining the overall time complexity of O(n). Another optimization involves early termination. If a node is already part of a flattened list and does not have a child, it can be skipped without further processing. This reduces unnecessary overhead and ensures that the algorithm focuses only on nodes that require modification. These adjustments can make the solution more robust and adaptable to different scenarios. Here, we begin by defining the structure of a node in the multilevel doubly linked list. Each node has a value, along with pointers for its previous, next, and child nodes. This child pointer is what introduces the multilevel nature of the list. Next, we define the flatten method in the solution class, which will take the head of the list as input and return a flattened version of it. The first step in this method is to handle the edge case where the head is none, in which case we simply return none. To help us traverse and manage the multilevel structure, we use a stack. We start by setting the current pointer to the head of the list and begin iterating through the nodes. Whenever we encounter a node that has a child, we need to process it. If the current node also has a next node, we push that next node onto the stack to save its position for later processing. Then, we connect the child node to the current node by updating the next pointer to point to the child and setting the previous pointer of the child to point back to the current node. Finally, we remove the child link by setting it to none, ensuring the structure becomes linear up to this point. Now, to handle cases where we reach the end of a level but still have nodes saved in the stack, we check if the current node's next pointer is null and if the stack is not empty. If that's the case, we pop the top node from the stack, which represents the next node to process. This node is then connected to the current node by updating the next pointer of the current node and the previous pointer of the popped node. After reconnecting the nodes, we move the current pointer to the next node in the flattened list. This loop continues until all levels of the list are processed, and the stack is empty. Finally, we return the head of the flattened list, which now represents a single-level doubly linked list with all the nodes connected sequentially. Here, we start by defining the node class, which represents each node in our multilevel doubly linked list. Each node contains an integer value, a reference to the previous node, a reference to the next node, and an optional child node. The constructor initializes these values, setting the references to null by default. Next, we move on to the solution class, which contains the flatten method. This method is responsible for converting the multilevel doubly linked list into a single-level doubly linked list. First, we handle the base case. If the head of the list is null, we simply return null. To manage the traversal and flattening process, we use a stack to temporarily store nodes that we will revisit later. We then initialize a pointer, current, to the head node and enter a while loop that continues as long as current is not null. Inside the loop, the first case we address is when the current node has a child. This is where the core flattening logic begins. When the current node has a child, we first check if there's a next node. If it exists, we push that next node onto the stack, as we'll need to revisit it after processing the child nodes. Then, we connect the child node to the current node by setting the current node's next pointer to the child. We also update the child's previous pointer to point back to the current node, establishing the bidirectional link. Once the child is connected, we remove the child reference from the current node to maintain the flattened structure. After processing the child, we handle the scenario where we've reached the end of a level but still have nodes left in the stack. If the current node's next pointer is null and the stack is not empty, we pop the top node from the stack and reconnect it as the next node. This ensures that we continue processing the remaining nodes from the higher level. Finally, we move the current pointer to the next node and continue the loop. Once the loop completes, we return the modified head, which now points to the fully flattened list. In this example, we start with a simple multilevel doubly linked list where node 2 has a child pointing to node 4, and node 4 is connected to node 5. The algorithm begins by initializing the current pointer at node 1 and an empty stack. Processing starts at node 1, where we see that current.child is none, so we simply move to the next node, which is node 2. Now at node 2, we observe that current.child points to node 4. To handle this, we push current.next, in this case, node 3, onto the stack. We then update current.next to point to current.child, which is node 4, and set current.child to none to sever the child link. Additionally, node 4's previous pointer is updated to point back to node 2. Finally, we move to node 4, which is now current.next. Now at node 4, we see that current.child is none, so we move to current.next, which is node 5. At node 5, both current.child and current.next are none, so we pop the top of the stack, which holds node 3. This node is set as current.next, and we also update node 3's previous pointer to point to node 5. We then move to node 3, which is now current.next. Finally, at node 3, we confirm that current.child is none and proceed to current.next, which is none, completing the traversal. The flattened list is now 1, 2 to 4, 5, 3. Next, we examine a slightly more complex example where nodes have nested children. In this new example, node 2 has a child pointing to node 4, and node 4 has its own child pointing to node 5. We start by initializing current at node 1 and an empty stack. Beginning at node 1, we observe that current.child is none, so we move to current.next, which is node 2. At node 2, we see that current.child points to node 4. To handle this, we push current.next, node 3, onto the stack. Then, we update current.next to point to current.child, which is node 4, and set current.child to none. Additionally, node 4's previous is updated to point to node 2. Moving to node 4, we find that current.child points to node 5. Here, we push current.next, which is none, onto the stack. Next, we update current.next to point to current.child, which is node 5, and set current.child to none. Node 5's previous is updated to point to node 4, and we move to node 5. At node 5, both current.child and current.next are none, so we pop the top of the stack, which holds none, and return to node 3. At node 3, we confirm that current.child is none and proceed to current.next, which is none, completing the traversal. The flattened list in this case is 1, 2 to 4, 5, 3. Now let's consider an example where the list is already flat, with no child pointers at all. In this example, the input list is completely flat, with no children. The algorithm begins by initializing current at node 1 and an empty stack. At node 1, we observe that current.child is none, so we simply move to current.next, which is node 2. At node 2, we again find that current.child is none, so we move to current.next, which is node 3. The process continues at node 3, where current.child is still none, leading us to move to node 4. Finally, at node 4, both current.child and current.next are none, so the traversal ends. Since the input list was already flat, the output remains unchanged, 1, 2 to 3, 4. The time complexity of the flatten function is O, n, where n represents the total number of nodes across all levels of the multilevel doubly linked list. This is because the algorithm ensures that each node is visited exactly once during the flattening process. To understand this, consider how the algorithm works. The current pointer sequentially traverses the nodes at a given level. When it encounters a node with a child pointer, the algorithm processes the child sublist first, while temporarily storing the next pointer of the current node in a stack. Once the algorithm finishes traversing the child sublist, it pops the next pointer from the stack to continue processing the parent list. Since operations like updating pointers and manipulating the stack are constant time, the overall complexity remains O(n), as each node is visited and processed just once. Now let's examine the best, average, and worst-case scenarios for this algorithm. In the best case, all nodes are already on the same level of the list, meaning no child pointers exist. Here, the traversal is straightforward and linear, with a time complexity of O(n). For the average or worst case, nodes contain arbitrary child pointers, causing the algorithm to switch between levels using the stack. However, even in these scenarios, every node is still visited only once, so the time complexity is O(n). Moving to space complexity, it depends on the structure of the multilevel list. In the worst case, where the list is a single vertical chain of nodes with only child pointers, the stack can grow to size n, leading to O(n) space complexity. In the best case, with no child pointers, the stack is unused, resulting in O(1) space complexity. Typically, for a balanced multilevel list, the stack holds at most one node per level, giving a space complexity of O(d), where d is the maximum depth of the list. When compared to a brute force approach, the optimized approach we've implemented shows clear advantages. A naive brute force method would involve recursively traversing each level and concatenating sublists, which could lead to repeated passes over the list. This would result in a worst-case time complexity of O(n²) and a space complexity of O(d) due to the recursion depth. In contrast, our iterative approach with a stack ensures that each node is visited only once, achieving a time complexity of O(n). Furthermore, by using an explicit stack, we eliminate the need for recursion, maintaining the same space complexity of O(d), without the additional memory overhead associated with recursion. Mathematically, this is justified because the number of operations is directly proportional to the number of nodes, n. The stack temporarily stores references to next nodes, and in the worst case, it holds all nodes, resulting in O(n) space. However, for most multilevel doubly linked lists, the stack size is limited by the depth of the structure, giving us a typical space complexity of O(d). When working on this problem, there are a few common mistakes to watch out for. First, developers often ignore edge cases. For example, you might forget to handle scenarios like an empty list, nodes that don't have children, or lists with several levels of nested child nodes. This usually happens because the focus is on solving the core logic, and boundary cases get overlooked. To address this, always test your solution with edge cases, such as null inputs, lists with a single node, or deeply nested child structures. Another common issue is modifying the list incorrectly. This happens when the doubly linked list structure is broken, often because both the previous and next pointers are not updated properly. Since this list is bidirectional, you need to ensure all pointers are adjusted carefully while flattening any child lists. Lastly, recursion can lead to a stack overflow if the list is deeply nested. While recursion feels natural for problems like these, it's important to consider the risks. If you're dealing with a highly nested structure, iterative approaches or tail recursion optimization can help avoid exceeding the call stack limit. Now, let's look at two more pitfalls. One mistake is not restoring the child pointers. After flattening the list, leaving the child pointers intact can lead to an incorrect structure. This often happens because it's easy to forget that these pointers should be set to null once the child nodes are appended to the main list. A simple fix is to explicitly set the child pointer to null after you've handled the child list. Another issue arises when the flattening order is confused. This can happen if child lists are appended in the wrong order, such as being added at the end instead of the correct position. This mistake is typically due to misunderstanding the traversal order. Remember, the correct approach is depth-first search, which means you should process child nodes before moving on to the next sibling. Following this order strictly ensures that the flattened list is structured correctly. In interviews, understanding the nuances of this problem can set you apart. First, recognize that this task is essentially a variation of tree traversal, specifically a pre-order depth-first search, but applied to a doubly linked list. Drawing this analogy can simplify your approach. Additionally, be prepared to clearly explain how you'll maintain the doubly linked structure during flattening. Interviewers value clarity and your attention to detail. It's also helpful to discuss trade-offs. For example, while recursive solutions may be simpler to implement, they come with the risk of stack overflow for deeply nested lists. On the other hand, iterative solutions are more robust but require careful management of auxiliary data structures, like a stack. Finally, emphasize optimization. You can achieve O(n) time complexity by avoiding redundant traversals. Using a tail pointer to track the end of the flatten list is one way to ensure that you don't repeatedly traverse already processed nodes. This problem also connects to several related problems that can help reinforce the concepts. For instance, problem 430 itself involves flattening a doubly linked list with child pointers, making it a direct application of the techniques we've discussed. Problem 114, which involves flattening a binary tree to a linked list, is a similar concept but applied to a tree structure instead of a doubly linked list. Another related problem is 426, where you convert a binary search tree into a sorted doubly linked list. This problem focuses on in-order traversal but still deals with the doubly linked structure. Lastly, problem 138, which involves copying a list with random pointers, is another challenge requiring manipulation of complex linked list structures. Exploring these problems can deepen your understanding of linked list operations and traversal techniques. Finally, it's useful to consider alternative approaches to solving this problem. The recursive depth-first approach is a natural fit due to the hierarchical structure of the list. It's straightforward to implement but comes with the risk of a stack overflow if the list is deeply nested. If you want to avoid recursion, the iterative depth-first approach is a great option. It eliminates the risk of stack overflow and is robust for handling large inputs, but it does require a stack or similar data structure, which adds to space complexity. Another effective method is the two-pointer approach. This technique is efficient in terms of time complexity because it avoids redundant traversals. However, it's more complex to implement, as you need to carefully manage all pointers to maintain the doubly linked list structure. Each of these approaches has its pros and cons, so choose based on the constraints and requirements of the problem you're solving. Great job working through this problem. We've explored both recursive and iterative solutions for flattening a multilevel doubly linked list and discussed their trade-offs. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and stay tuned for more exciting coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!